Okay, let's jump right into this explainer. If you're a BMRIT student, you already know the ultimate enemy of clear clinical radiography. It's blurry, scattered images. Seriously, if you've ever looked at a radiograph of a thick body part, like a pelvis or an abdomen, and wondered why it looks like it was photographed through a ridiculously thick fog, well, you've encountered our main adversary today. So we're going to break down the actual mechanics of image sharpness. We'll explore how the early imaging pioneers fought back against all that image-degrading noise, and more importantly, how you can manipulate physics on the clinic floor to produce crystal-clear diagnostic images. Here is our roadmap for today. We are covering the Compton scatter problem, anti-scatter grids and ratios, grid types and cutoff, the air gap technique, resolution and artifacts, and of course, our key takeaways. Starting with Section 1, the Compton scatter problem, basically the absolute enemy of contrast. So when an X-ray beam enters a patient, especially if you're using higher KVP settings or imaging larger patients, a massive chunk of those photons undergo what we call Compton scattering. Now, proper beam collimation is definitely your first line of defense to limit the exposed tissue area. But the photons that do enter the patient often interact with outer shell electrons in the soft tissue. They literally eject the electron and then bounce off in totally random directions, kind of like a pinball. The real issue here, some of these scattered rogue photons still manage to hit your digital detector. But since they didn't travel in a straight, clean line from the X-ray tube, they carry absolutely zero useful positional information. They don't show you anatomy, they just act as this annoying image-degrading fog that completely washes out your contrast. So, the big question is, how do we actually rescue our diagnostic contrast from all this fog? Well, that exact question is what drove Gustav Bucke way back in 1913 to figure out a way to filter out the noise. He realized that we needed a mechanical solution, a physical barrier sitting right between the patient and the detector that could somehow magically tell the difference between a good, straight primary photon and a bad, bouncing, scattered photon. Let's dive into how he did it in Section 2, Anti-Scatter Grids and Ratios, our mechanical solutions. Bucke's brilliant invention is the anti-scatter grid. Think of it kind of like a set of incredibly tiny, microscopic window blinds. Grids use these alternating vertical strips of super dense lead, which are separated by radiolucent inner spaces. Those inner spaces are made of stuff X-rays can pass right through, like wood, aluminum, or organic fiber. The primary radiation, the good X-rays coming perfectly straight from the focal spot, sails cleanly right through those inner spaces to hit the detector. But the scattered radiation, which is flying in at these crazy, oblique, slanted angles, crashes straight into the lead strips and gets completely absorbed. For your BMRIT exams, you absolutely must commit this formula to memory. Grid ratio equals H, the height of the lead strips, divided by D, the distance or width of the inner spaces between them. But here is where we hit the ultimate trade-off in radiography. Take a look at a 10-to-1 grid ratio, for example. Sure, you get incredibly high scatter rejection and beautifully crisp contrast, but it comes at a massive cost, which we call the Bucke factor. Because that grid is physically sitting there blocking so many photons, both good and bad, you actually have to increase the radiation exposure by 4 to 5 times just to get enough of a signal to reach the detector. It's a huge deal. You increase the grid ratio for better contrast, and you significantly increase the radiation dose to your patient. It's a constant daily clinical balancing act. Moving right along to Section 3, grid types and cutoff. Because alignment really matters.
Now, not all grids are built the same way. Parallel grids are definitely the simplest. All the lead strips just run straight up and down. But remember, an X-ray beam naturally diverges, right? It spreads out from the tube in a cone shape. This means the primary beam at the far outer edges of your field is actually traveling at an angle. So it's going to crash right into those vertical lead strips of a parallel grid, causing what's known as edge cutoff. To fix this, engineers created focused grids. Here, the lead strips are progressively angled from the center out to the edge, perfectly matching that natural divergence of the beam. This is your modern clinical standard. You might also run into crossed grids occasionally. Those are essentially 2 parallel grids layered on top of each other perpendicularly. They offer extreme scatter cleanup, but man, they are incredibly restrictive if you need to angle your tube even a little bit.
The thing about focused grids is that they absolutely demand perfection. If you misalign a focused grid, you get grid cutoff. This happens when your grid starts absorbing the good primary radiation instead of just the scatter. If the grid is tilted even slightly, that's an off-level error. Using a focused grid at the completely wrong distance from the X-ray tube, that's an off-focus error. And if your central beam isn't perfectly centered right on the middle of the grid, you've got an off-center error. Clinically speaking, grid cutoff is a total disaster. It means repeated exams and consequently doubling the patient's dose. It usually shows up on your radiograph as a really bright, highly underexposed band started down the center, or sometimes you just completely lose density on one side. Bottom line, if you see uneven density, check your alignment immediately. Now, Bucky's original grid did work, but it had a really annoying flaw. It left these highly visible white lines all over the image, exactly where the lead strips blocked the beam. Luckily, a few years later, a guy named Hollis Potter made a genius improvement, the Potter-Bucky diaphragm. He engineered a mechanism that actually makes the grid rapidly move and oscillate from side to side during the exact moment of exposure. By doing that, the grid lines are completely blurred out and totally invisible on your final image. This moving grid system is pretty much the standard in almost every modern table and wall stand unit you're going to use.
All right, Section 4, the air gap technique. Let's talk about using distance to our advantage.
The air gap technique is super clever because it completely sidesteps the physical grid altogether. Instead of shoving hardware between the patient and the image receptor, we just use raw physics. We increase the physical distance between the patient and the detector. Because scattered photons travel out at these really severe, crazy angles, if you literally just move the detector far enough away from the patient, that scatter will diverge right out into the room and completely miss the detector. It works beautifully for certain specific exams, like lateral cervical spines. However, there is a catch. Increasing this object-to-image distance, or OID, automatically introduces geometric magnification and blur, which we call penumbra. So it's a fantastic tool, but definitely one you have to use selectively.
On to Section 5, resolution and artifacts, the ongoing quest for achieving total image clarity.
Spatial resolution is basically your ability to clearly see closely spaced objects as completely separate, distinct entities. If you want to tack sharp image, you need a few things. You need a small focal spot, you need optimal distances, and by that I mean a nice long source-to-image distance and a really short object-to-image distance, and you need a digital detector with incredibly tiny individual receptor elements. We measure this ultimate sharpness in line pairs per millimeter. In a typical modern digital flat panel detector today, you are generally looking at achieving about 3 to 5 line pairs per millimeter of absolute clarity.
As a technologist, you literally have to memorize these image quality killers. An artifact is just any weird feature on the image that mimics or obscures real pathology but doesn't actually exist inside the patient. Motion blur, like when a patient breathes or moves, is definitely the most common. You might also spot visible grid lines if your Potter-Bucky mechanism randomly fails to move. In digital radiography, you can actually get something called ghosting. That's where a residual electrical charge from the previous patient's exam faintly shows up on your brand new image. And finally, you absolutely must look out for quantum mottle. This looks like heavy graininess, almost like static all across the image. It happens when your radiation dose is so statistically low that there just aren't enough X-ray photons hitting the detector to create a strong uniform signal.
And that brings us to Section 6, key takeaways. Let's do a quick summary.
Here is your master checklist for understanding image sharpness. Lock these in. Number 1. Anti-scatter grids are absolutely essential for absorbing scatter from thick body parts, but they fundamentally require you to bump up the patient's radiation dose. Number 2, the grid ratio, that's H/D, dictates exactly how aggressively that grid is going to clean up the scatter. Number 3, always ensure your focus grids are perfectly aligned. Remember, grid cutoff is going to cause bright, underexposed bands of uneven density. And lastly, always be on the hunt for artifacts like quantum mottle and motion, because they can so easily be mistaken for real pathology. Take these points with you. They're your definitive guide for mastering radiographic image quality. As you get out there and step into real clinical practice, I want to leave you with a real thought experiment. You now know that to get the absolute highest contrast, most beautiful image, you could just throw a high ratio grid on there. But you also now know that doing so literally pumps 4 to 5 times more radiation into the actual human being lying on your table. So how are you going to navigate that choice? Mastering radiography isn't just about memorizing some physics formulas to pass a test. It's about mastering that delicate, everyday balance of clinical responsibility, pushing the limits of our imaging tech while always minimizing the radiation dose to your patient. Keep that in mind the very next time you set your exposure. Thanks for joining me on this explainer, and keep learning out there.